So I'd like to thank the organizers and Ignacio in particular for invitation. So I'm guessing that my talk is probably the only kind of experimental talk for this conference. So that's why I will start maybe gently. So like, as many of you know, there is like a growing world. There is a community of scientists and engineers who are trying to build quantum machines, like quantum computers. And this effort can be viewed as a kind of quest for controlling quantum world, where we first isolate and start with some kind of simple quantum objects and learn to control them, and then put them together to build more and more complex systems from them. And the hope is that with this kind of systems, we can explore new physics. And usually this is like an engineered many-body entangled states, but also eventually start kind of exploring new applications, like, for example, quantum computing. So this is an exciting field that you read about almost daily in newspapers, but this field still faces big challenges. And one of them is that right now we really don't know if and how truly large scale, for example, quantum computers can be built. I mean, so we are making progress, but nevertheless there are a lot of questions remaining. And moreover, even if we were to build some of them, it's actually not so clear, how we can use them. So this kind of application challenge is even kind of more severe. So there was, for example, talks already about quantum algorithms and so on. We need more of them. So nevertheless, as I already mentioned, it is an exciting field because there are now many physical systems which are being used to actually, build some small quantum computer prototype. And I would say the big challenge now is to really somehow bridge two contradictory forces of nature. One of these forces is controllability. So like in a lab, in our lab and also in other labs, we have systems of few quantum bits which we can isolate and control extremely well and keep quantum mechanical. But of course, to make them kind of interesting and useful, we need to, have many more of them. And, usually if you take a lot of quantum objects and, throw them together, this kind of system loses quantum character, right? It behaves classically. This is this kind of force of nature which we really need to kind of circumvent. We need to learn how to, by making system bigger, we can still have this kind of stability and control. So the current state of the art is that, in a couple of these platforms, people can put together systems of, 100 now, maybe a few hundred of quantum bits. And, potentially some of these systems can do tasks which, at least exactly classical computers cannot simulate. And so basically the idea now is we can start using this type of, small or medium scale systems to try to learn enough to build bigger and in particular better quantum computers, but then also try to kind of address this application challenge. So I will focus today on one specific set of projects in our lab in which we build quantum computers from isolated neutral atoms. So this is the image of something which is called magneto-optical trap. So this is how all of these experiments start. You basically start with the cloud of atoms in a vacuum, which are basically nearly motionless. So we kind of know how to slow them down using laser light. So they're basically sitting still, and basically it's not uncommon to start these things with, experiments with, tens of millions of atoms. So there's actually plenty of qubits if we were to able to control this atom, one atom at a time. But so basically, what it really means is that the source of cold neutral atomic qubits is essentially kind of unlimited. All we need to do is to learn how to control these atoms. So kind of this was a motivation. A couple of years ago, we started kind of a new approach to building these controllable quantum systems, where we basically literally, build them, atom by atom. And the way how we do it is we use these optical tweezers, these tightly focused laser beams, which can attract and hold individual atoms. So we typically start these experiments not just with one, with many, but we focus these atoms so tightly that each of these tweezers can hold at most one atom. And so usually when we try to trap many atoms, what will happen is that system will have some entropy because some traps will be filled and some will be empty. So to get rid of the entropy, what we literally do, it's a classical entropy. We just take a picture of the atoms, figure out which traps are full and which are empty, and then basically rearrange. Once we know where atoms are sitting, we can rearrange them kind of in any desired configuration. And so with that, we end up with systems of atoms which are sitting typically a couple of micrometers away from each other. And at this point, they don't talk to each other. The interaction is negligible. They also don't tunnel, between these different lattice sites. So to make them interact, to entangle them, what we do, we excite these atoms into the Rydberg states. We change the principal quantum number in a highly controlled way, how I will explain in a second, and make them interact. That's how we do, for example, quantum logic operations. So let me just talk a little bit more about this kind of Rydberg excitation, because this is the central component of this entire approach. So we like Rydberg states for two reasons. So first off, they have relatively long lifetimes. They live typically for hundreds of microseconds. But in particular, they have very strong interactions. So for example, if we excite the atom in a state with n equals 100, the van der Waal interaction between these atoms will be 14 orders of magnitude stronger than those between the ground state atoms. And so it's a large number, so we can make a good use of that. So one way to do that is to utilize this effect which is called Rydberg blockade. So the way how it works is the following. So what you do is basically you take a highly coherent laser and tune it into the transition from the ground state into certain Rydberg state with certain selected principal quantum number. And so if the atoms are far away, then this resonant interaction would just drive independent Rabi oscillations. But if these atoms come together, then eventually this strong interaction will take over, and past certain distance, what will happen is that you will be able to excite one atom or another, but never both. So the simultaneous excitation will be blocked at distances smaller than this blockade radius. And actually, it turns out that this is an exceptionally good mechanism to entangle atoms and do quantum logic, because at this point, this basically entangling mechanism is insensitive to exact position of atoms. It's also insensitive to the motion. So in a way, it becomes kind of digital. If the atoms are far away, they don't interact. If they are close, they basically interact with nearly infinite strength, at least to the leading order. And so this is actually kind of, as you see, a relatively old idea that kind of initially we started thinking about with Ignacio and some other people. But basically by now, this actually is exploding field. And so in what follows, I will show you, some experimental results. What we will be doing is we will be assembling arrays of these atoms, changing the internal states by using lasers. Sometimes we excite them in Rydberg states. Sometimes we will change the atomic spin state. And then eventually, after the evolution, we will make we'll take another picture of atoms, but in this case, we will take it in a state-dependent way. So we'll basically, if atom is in one state, we'll see the kind of some light coming, and if the atom is in another state, there will be none. And so, as I already mentioned, so this is actually now kind of extremely rapidly developing fields. There are a couple of hundred experiments of this type under construction. There are at least 8. I think there are more now companies which are trying already to commercialize this technology. And basically, what's kind of exciting is that starting from these basic ingredients, you can now try to use different types of, for example, atoms, different types of atomic species. You can also try to combine these optical tweezers with optical lattices is another approach. So when people start also using, for example, molecules, and so these are some kind of exotic, systems. People, for example, use 2 different species of atoms. So this is actually a picture from Hannes Bernian lab in Chicago. And you can now trap a few thousand, over 5,000 atoms. This is from Manuel Andres' group at Caltech. And what's cool is that actually with this kind of approach, you can really sort of explore very different directions, starting from maybe body dynamics and quantum computing that I'll focus on today, to quantum metrology. For example, people use it to build atomic clocks, and you can build quite exotic clocks. So perhaps one can really someday probe real quantum gravity with this. techniques. Okay, maybe, but it's also complementary to many other things which is happening in the community, in particular to optical lattices. And kind of there are there are various practical considerations depending on application you want to do. You could either pick different type of atom, like alkali atoms that I will focus on. We'll just have one electron orbiting active, but for clocks and metrology application, alkaline earth atoms are preferable. Molecules can also be quite interesting also for some fundamental physics kind of measurement. But even once you pick the atom, you have a lot of flexibility. For example, you can encode qubit in superposition of ground and Rydberg state, or you can encode it in a superposition of hyperfine state. These are the spin states of atoms, and only excite them in the Rydberg when you want. But even once you pick the encoding, you still have a possibility to either do quantum evolution in kind of analog way, or digital, or hybrid analog digital, or as you will see, even like fault tolerant. So basically, using quantum error correcting code. So this is a little bit, like how we actually build and control these arrays. I put these slides in because Juan always asks me questions about holography, and last time even Ed asked me about how special light modulators work. So basically what this is, a special light modulator, is it's a computer-generated hologram, which basically by reflecting the light and putting some kind of phase profile, you can generate, like some, deflection, and you can, for example, using this approach, you can generate this arrays in 2 dimensions of these beams. So basically what we do, we project them in the vacuum chamber, and this way you can create like tens of thousands of tweezers right now. So this special light modulator is amazing because you can basically program almost arbitrary pattern, and make it extremely homogeneous. There's only one drawback, is actually slow. So to move atoms around, to sort atoms, and you will see that moving atoms will also play a big role in the future talk. So we use a second channel, and here we use this device called acousto-optic deflector. So basically, here you send the sound wave, and it deflects the light. For each tone of the sound wave, it deflects it by a different angle. And we use 2 of them, so it's such that we can move rows and coulombs of the atoms independently. It's all computer controlled. So that's basically kind of the basis for our 3rd generation system at Harvard. So basically, in this 3rd generation, we have now larger systems, high fidelities, more advanced control. So basically, we can, create arrays, of over 500 atoms without defects. And basically, with this type of system, is actually a lot of fun. You can really explore different directions. So as I already mentioned, you can think about analog dynamics, creating new phases of matter, studying. So many body scars were mentioned, yesterday. So actually first discovered in this kind of atom arrays, and we continue to explore them. So related to this morning's talk, one can also create this topological spin liquids, kind of toric code type, and study them. You measure these string operators, even measure entanglement entropies. So and I will, in what follows, I'll give you a little bit of sampling of kind of work along different directions. So I will start first with analog approach, and basically involving studying the kind of dynamics. So kind of the idea here is the following. So suppose what we do is we basically start with certain geometrical patterns. So these are atoms. In this case, they are in a square lattice. And what we do then, we can basically determine the Rydberg blockade radius. So for example, suppose here we just make sure that only nearest neighbors are blocked. So in this case, basically, you can describe the system as an effective spin model. So it's becomes a spin 1/2 system with ground and Rydberg state of few active levels. So this laser driving would be like a field in X direction. So the laser detuning is like a field in the Z direction, or if you want a chemical potential. So N is number of Rydberg atoms on each lattice site. And then you have, of course, the interaction. And what one can do is one can, for example, either explore a ground state phase diagram of this kind of system, of this spin model, or potentially you can study dynamics. And the way how one can do it is the following. So you can start with all atoms in the ground state, and pick this term, pick detuning negative, such that the atoms are really like should be in a ground state. So it's the ground state of this entire many-body system is all atoms in a lower state. And then suppose that what you do then, you slowly change this detuning from positive to negative. So if detuning is positive, you would like to maximize n. But if you have blockade, you cannot excite all atoms to the Rydberg state. So you'll only excite half of them because you cannot excite nearest neighbor. So you will create pattern like this. So this is actually an experimental image of one given experimental run, which is like a perfect antiferromagnetic state, right? So only every other atom is excited. So red is basically the atom is in the Rydberg state, So okay. So first off, this does not always happen. So if you do many runs, sometimes you will have patterns like this, but sometimes you will have domains, and you can, for example, you can introduce correlation functions and, study average, across many runs. You see, you basically have this density correlation, which spread over entire array in this case. You can also look at these images microscopically. So it turns out that this perfect antiferromagnetic state, even though not very frequent, still it's the most frequent of all. So this state and a kind of a state which is shifted by a lattice site away. And what you can also do, you can study, for example, dynamics by changing the speed with which you go across this phase transition. You can try to see, for example, how characteristic size of the correlated domains, grows. What in this case, for example, like it's a work from a couple of years ago, what we did, we basically used this kind of correlation growth as a function of the speed to prove critical exponents of this phase transition. So basically here, the system undergoes a quantum phase transition. It turns out to be Ising 2+1 phase transition. And the way how you can verify it is by just looking at this correlation growth at different speed, by rescaling it with the critical exponents, with certain critical exponents, you see that all of these curves collapse. So it's kind of this idea of universality of quantum phase transition. And basically from here, you can basically see that, what we really study, observe is this kind of 2+1 Ising quantum phase transition. So that's kind of a general kind of set of tools which we use for this analog dynamics. Maybe I should kind of slow down and see if there are any questions, right, before I go into details, Yeah. In principle, yes. So, and there are different ways to do it. So, first of all, typically these atoms we work with, they have multiple hyperfine states. So, and I will talk about using hyperfine states in a second. But you can also, of course, excite different Rydberg atoms, right? So in principle, you can have very large D, right? The question now becomes how well you can control it and so on, but in principle, yes. So, is everything else clear? All right, so don't hesitate to interrupt. So, okay, so what I will do next is I will basically just continue this sort of dynamics kind of discussion and focus on the example of recent work which we sort of have done, which explores this kind of dynamics of this phase transition beyond the Kibble-Zurich. And this actually is motivated by the, yeah. So no, in this example, we are at a very low temperature. So basically, this is kind of this quantum phase transition, technically zero temperature phase transition. And the system is isolated. But for example, if you go across this phase transition with finite rate, right, you create sort of an effective temperature, right? So you create, for example, you can sometimes interpret as creating an effective temperature. right? To what extent is a good approximation is not always clear because it's not guaranteed that the system formalizes. But that's so it's a technically zero temperature isolated system. I mean, of course, there will be errors during evolution. That's another, but it's generally very low temperature. And you can ask, for example, the question, about temperature of subsystem. For example, if you have a subsystem, then you have some, due to entanglement, there is some entropy you can assign temperature. So you can also, if you're non-adiabatic, you can also ask to assign temperature. So this is a kind of a setting, right?
Okay, so yeah, maybe it's a question. So
yeah.
In the experiment, what controls the effective temperature? So 2 and 1 give you.
So for huh? No, it's not a lab temperature at all. So okay. I mean, strictly speaking, the entire system here is isolated. So it's technically zero temperature, kind of from this purity set. But then you can ask various more subtle questions. And so, for example, you could say, well, what if you change this detuning and you change it relatively fast, right? You kind of inject energy in the system, right? So in principle, this amount of injected energy, if the system eventually thermalizes, you could use to sort of assign effective temperature, right? And so, like, for example, the way how it's characterized here is that you basically, by going with a different speed, your correlation length grows to a different value, right? And you could say, if the system was thermal, this correlation length you could potentially convert into temperature, but it's not always the case, and you will see it why, So because system will have still non-trivial dynamics after this transition, So and eventually, maybe in a long time limit, indeed it will somehow thermalize, So it's not, this thermalization is quite non-trivial, in a general setting, but there are even some specific states, like there's many body scars, which were mentioned. There are some specific states from which you start, where you see that, for example, even like for local subsystems, the entropy grows, not monotonically, it grows and then shrinks. So it's kind of, it can be these things, some weird things can happen, Does make sense? Yeah. Okay, so, all right, so basically, maybe a little bit, my next story is a little bit related to that. So, and it's also related to some kind of relatively simple intuition. So if you, for example, take like a water and try to kind of freeze it reasonably fast, lower temperature. So the way how this freezing will occur often is through the process which is called coarsening. So basically, coarsening is a kind of progressive growth of longer and longer range order. So it's known in the classical phase transitions starting in 1950s. And this coarsening usually kind of generates this so-called self-similar dynamics. So it kind of, involves evolution in time. It looks like basically zooming in. What you see, some fine structures become, larger and larger, but sort of the essence of the structure is preserved. And so this dynamics is often driven by this so-called local curvature of domain walls. I will explain it in a second. So this is classical Ising model simulations, and it's natural to ask, can you see coarsening near quantum phase transition? So in other words, connecting to the previous kind of slide, so if you do this ramp across a phase transition and you follow this so-called Kibble-Zurich dynamics, Kibble-Zurich dynamics says that basically, correlations will grow to a certain point after which dynamics will be frozen. And this clearly is not the case here, for at least in classical physics. So the question is, there will be some kind of phenomenon like this in quantum physics? And also, of course, it's interesting to try to probe it in highly controllable system, because you could try to explore directly microscopic origin and things like this. And actually, somewhat surprisingly, only very recently people started looking at this coarsening, near the quantum phase transitions. And in particular, there was a theory paper here by Princeton, by David and Ryan earlier this year. And actually, just recently, there was an experiment by Google AI group by using, Google quantum computer in an analog way for the first time to kind of study these effects. So let's see how we can explore it in our system. So what we'll do is follow the general recipe, what we talked about so far. So suppose we start with this 16 by 16 atoms, a square lattice. And what we'll do is we'll basically try to change this global detuning, ramp it across a phase transition to go from the state which is trivial to the ordered state. But what we'll do is following this ramp, we will stop it, and then we'll hold the system for some time and kind of allow it to maybe kind of undergo a little bit of this coarsening dynamics. And the way how it looks in practice is the following. So we start first in this phase, which is kind of called disordered. So where we just, there is no order clearly in the system. So if you kind of convert it into a anti-ferromagnetic domain, this basically, clearly there is nothing. But if we now cross the phase transition, so then what we see is that, you start, if you take a snapshot, you will see some anti-ferromagnetic domains in the system. And actually, if you wait longer, what happens is that this big ferromagnetic domain starts to grow and overtake the small ones, right? So your system clearly here, this order is, is growing. So clearly the coarsening is happening. So one can try to quantify it a little bit more. So you can, for example, look at correlation length. So clearly the correlation length, grows with some little bit funny oscillations, which I will return to. We also kind of can check, for example, depending where you park. If you park near the phase transition, then the correlation length grows faster. So you can also explore the self-similarity. So just take, kind of pictures depending on the waiting time and, look at the structure factor. And indeed, if you rescale it correctly, it kind of looks self-similar with some caveats, So basically, but very clearly, we see clear departure from this Keeble-Zurich mechanism. And there is some kind of form of self-similar dynamics, if it's not completely sort of universal, and that there is some scale remaining here. And then finally, as already mentioned, it appears that this correlation length, oscillates. So there is some kind of oscillation on the top. So let's try to kind of uncover and understand, what exactly is going on here. And in order to do it, we will actually use kind of, more sort of controlled state preparation. So in particular, we will now introduce this additional control knob. It will be like a local detuning. And so what with this local detuning we can do, we can prepare, for example, different patterns of anti-ferromagnetic states. So we can, for example, prepare one type of anti-ferromagnetic surrounded by another type, with the very well-defined domain wall. And we can, after preparing it, we can just release it and see how the system dynamics proceeds. So, and basically in this case, so these are pictures. What you see is that clearly this, this little domain disappears in a sea of this larger domain. And we can check it depending on how close we are to the quantum phase transition. So indeed, if we sit closer to the phase transition, this domain disappears faster. But also, if you look now visually how it disappears, it's not just it sort of diffuses altogether, but somehow the shape changes, right? So it started with a square shape, and here it's no longer this kind of square shape. So okay, so what's going on? So to understand that, what we can do, we can just prepare, two domains with this kind of zigzag domain wall. And if you look at this zigzag, what you clearly see is that this dynamics is faster during the points where the curvature is higher. And you can basically visualize it directly. So if you look at the points where, there is no curvature, then dynamics doesn't really, this domain wall doesn't move very much. But at the points where the curvature is largest, there is the fastest dynamics. And this is consistent with this kind of, dynamics, which is driven by local curvature. So it should scale like 1 over r. So what it really suggests is that if you look at the area of a system, the area should just change. The time derivative of the area should be a constant, basically a constant speed. And indeed, if we look at this area of these defects, indeed what we see is that indeed it kind of changes with this kind of at a constant, as a constant. And moreover, from here we can immediately extract this kind of velocity, which actually indeed, accelerates close to the phase transition, and in fact, it accelerates following this by this universal kind of scaling law, which is at least consistent with what's known for this 2+1 Ising phase transition. So, but if we now look at this dynamics a little bit more carefully, then what we see is that after this middle kind of structure disappears, you see that system still has some life, right? There is some kind of oscillation going on. And in fact, if we look a little bit carefully, we clearly resolve these oscillations, which I already pointed out. And moreover, this oscillation frequency depends on how close you are to the phase transition. And this is something which we did not anticipate, but it became very clear that something interesting happens as we close to the phase transition. So it turns out the origin of this oscillation is so-called amplitude, or sometimes people call it a Higgs mode, and this can be understood in this kind of mean field. So basically, you have kind of this Landau potential, mean field potential, where the system kind of oscillates, and after the phase transition, it will actually still oscillate in this two kind of local minima, but with the faster frequency, and this we can really test kind of quantitatively. So indeed, it kind of is consistent with like this frequency, just following essentially the energy gap associated with this quantum phase transition. And we can also extract the damping, which actually increases close to the phase transition, and also the fact that the oscillation now changes from kind of going around zero to going around the finite value. And so basically, one can really study this quantitatively. So this oscillation frequency, you can actually calculate using this MPS and TDVP approach. In fact, actually deviates from the mean field. It's closer to 1.9 versus square root of 2. But for example, the strong damping effects, is actually extremely challenging to capture for the classical methods, because you really need like close to the phase transition. There are a lot of levels you need to include. So basically, what you see is that we can, like by doing these analog simulations, we can really gain some insights into this quantum phase transitions. So, okay, so I will now switch to talking about different modalities, but maybe it's another kind of point where I can stop. Are there any questions about this? So in this analog model, basically what we have is we have a very natural system Hamiltonian, which we can just directly sort of implement, and we can look how, preparing different states, we can look how the dynamics proceed, and we can study, for example, these questions about different types of phase transition, not just Ising, but that's a kind of, and dynamics is maybe the most interesting. Yes. Yes. Well, there are some set of Hamiltonians which we can implement, but for example, by just controlling the Rydberg blockade radius, we can, for example, explore a wide variety of different phase transitions. So this is a second order Ising transition, but for example, we can access first order transitions. We can also look at transitions in different universality class. So this is all possible, within kind of limits, right? Yes. Okay, so, all right, so maybe with this, I will kind of switch to another modality. And this is kind of maybe more conventional in a kind of quantum computing. These are these kind of called digital processors, where basically you build your dynamics from quantum gates called quantum operations. There is kind of a new way to do it, which we actually sort of started to explore a couple of years ago. We call it reconfigurable quantum architecture. So what I have told you so far is that we basically, prepared certain arrangement of atoms, froze the atoms, and then turn on quantum dynamics, turn the interaction between atoms. But it turns out that we can also do things differently. Specifically, if we encode the quantum information in these hyperfine states of atoms and the spin states of atoms, we can not only store it for a very long time, but we can also move atoms around without destroying quantum bits. And this gives rise to this so-called reconfigurable architecture where you can start with a certain arrangement of atoms, do some excite them in Rydberg state, do some operations, and eventually bring qubits down to these hyperfine states, change the connectivity, change the position of the atoms, change the connectivity of the system, then turn the dynamics again and proceed in this way. So that's kind of the idea of this reconfigurable architecture. And so there are two important features. So first off, it becomes non-local immediately. But in particular, it actually allows us, as you will see, to really do some very parallel, very efficient control over these kind of atoms, over the dynamics, in a way which is really quite unique. So there are different types of things which we are sort of exploring with that. So for example, you can think about this kind of analog digital hybrid dynamics. So for example, you can start with this analog dynamics, let the system evolve, and then stop the evolution, bring the atoms to hyperfine states, and then do some digital operations. So for example, what you can do, you can measure entanglement entropy using this way. So for example, in this case, we use a two-copy method of the system to basically measure this half-chain entanglement entropy. So you can also start, kind of introducing various tools for many body physics. As you already have seen, we can sort of locally, for example, change properties of the system. So there are some ideas how to kind of apply it to simulating, quantum chemistry, which is known to be like highly non-local problem. So I will maybe mention a little bit, simulations of topological matter if I have time at the end. But actually, we're also starting to think how to at least explore toy models of this ADS CFT. So for example, you can think about sort of using kind of mirror network to create sort of a kind of a boundary critical state, allow for it to evolve and then kind of use kind of mirror in reverse to disentangle it. And it's kind of some of the ideas we're exploring with Jordan, for example. So all of this is actually very cool, and I think there are a lot of cool possibilities, but there is one important challenge, is that all of these ideas, all of these approaches are fundamentally bound by the errors that you make in quantum operations. So this, if you do rotation of a qubit, in particular if you entangle qubits, you always make small error, and that just limits the degree to which you sort of have a meaningful result. So this is something which has been known in the community since early days. And in the beginning, even people sort of thought that could be a reason why quantum computers can never be built. But then this idea of quantum error correction has been sort of discovered. And this quantum error correction kind of uses a very similar idea to classical error correction, basically uses redundancy. For example, instead of just encoding qubit in one sort of degree of freedom in one atom, you can use, for example, 3 atoms and use kind of majority voting. So that's how classical error correction codes works. To make quantum error correction is actually quite non-trivial, because there is non-cloning theorem. You can also not measure without destroying quantum information. But nevertheless, it turns out that you can do quantum error correction, and the way how you do it is by just basically taking your so-called logical qubit and delocalize the information between several physical qubits. And so, after this, what you can do, you can measure the so-called stabilizers, to basically detect local errors without destroying the entire state which was stored here. And because this information is stored non-locally, if something happens to one of these qubits, so basically it does not destroy this logical information. So by being delocalized, logical qubit degree of freedom is hard to accidentally manipulate. And I would say already the fact that it's theoretically possible to do that, it's already kind of amazing. But as you see experimentally, is quite hard. So here is an example. It's probably the most famous quantum error correcting code, and the advantage is you've seen it already this morning. So in Mikhail Lukin's talk, he talked about this toric code or surface code by Kitaev. So the way how it works is just a kind of a patch of basically of qubits, they're called data qubits. And then what you do to basically protect the information, you use these local checks. You could either measure products of 4 z's around the vertex or products of 4 x's around the blockade. And so basically this surface authority code turns out to be like a product of effectively 2 repetition codes, one for x errors and for zeros. So basically, in this case, you can encode 2 logical operators, which are products of z's along one, for example, going from right to right, and x's from top to bottom. And the idea is that basically for error-free state, all of these checks, all of the stabilizers should be +1. So if one qubit, for example, here flips its state, by measuring 2 stabilizers and seeing that they have value -1, you can immediately, so in this case at least, localize the error, and then you just can go and flip this qubit back. So, and kind of the general idea here is that if you make this lattice bigger, so you have more checks, but of course you also have more opportunities to make an error. So it turns out that there is a kind of a threshold behavior. There is a phase transition. So basically, if the error probability is smaller than certain threshold, which actually for this case is about 1%, then you can suppress the error by just growing what people say code distance, by basically growing the size of this code. And so this, in principle, opens a realistic route towards extremely small errors. And it was really this theoretical breakthrough which caused the field of quantum computing to take off. So we know that eventually we need to switch to these performing algorithms with logical qubits rather than physical. But you also see it's actually quite challenging because there is quite a bit of overhead for each. Now, for each qubit, you need to have like a big array and kind of do all of these sophisticated operations. And for this reason, up to very recently, basically the largest kind of demos were limited to 1 or 2 kind of small logical qubits. So we already, like a couple of years ago, we realized that using this reconfigurable architecture offers some kind of very promising route towards that. And so this actually is the work from 2022, where we made a Tori code on the torus. So the way how we did it is we started with an array of stationary qubits, and then we have this moving ancillas, which make this stabilizer measurement. And you see that in one of these last move, we move these ancillas all the way around this array, and basically that allows us to actually close the torus. So, and okay, that's already cool, but what's important is that this entire circuit was programmed by specifying the special light modulator profile and basically 2 voltages which control AOD. One is going up and down the beam, and another one is going left and right. So this kind of efficient control turns out to be super important as we try to do more and more complex circuits with logical qubits. So okay, so last year we were quite busy with kind of improving technical aspects. So for one thing, we improved our 2-qubit gate fidelity so that it's now below the threshold for quantum error correction. We also now can implement fully programmable parallel single qubit gates. Again, we use these 2 acousto-optic deflectors to now shine different patterns of the light, which actually changes hyperfine states of atoms. And we also have the ability now to read out qubits in the mid-circuit by just plucking some of the qubits, moving in the separate zone, and just imaging them with the focused laser beam. So combining this, all of these kind of ingredients, we implemented this kind of first logical quantum processor. And so actually, if you it's a schematic, but you kind of starts looking like a computer. So it has a storage zone where you store these qubits. It has a kind of entangling zone where you do logic. You have this readout zone. So it's actually kind of reminiscent of the early days of something which is called Wien-Neumann architecture. It's actually, for some reason, there is a version called Harvard architecture. So it's, I think, between, one of them was at Princeton, right? So. You kind of, Juan, you defected anyway, so that doesn't count. So okay, so but okay, so the key idea of this entire kind of approach can be understood by just looking at one experiment, and that is making the quantum gate between 2 logical qubits. And so suppose you have two surface codes in which you stored quantum information. It's now delocalized. And usually to do the quantum operations between the two of them, so what you need to do, you need to basically, because the information is delocalized, you need to have each basically physical qubit on the right somehow feel the presence or experience or check the state of the qubit on the left. And so, and this can be done, for example, by braiding the excitations or by something which is called lattice surgery. But all of these operations are actually quite non-trivial. And in fact, in order to do them, you need to do many errors, many rounds of error correction, which is typically proportional to something which is called code distance. Instead, in our approach, what we can do is very simply take one of these patches and bring it literally on the top of another patch, and then perform something which is called transversal synod. So basically what you do the gates between each pair of the qubits, which are sitting on the top of each other, right? And then you just do the gates in parallel, and then you separate these patches again. So this implements a logical synod. So there are a few very important features. So for example, this logical synod is inherently fault tolerant because the interactions between the qubits, physical qubits, are kind of local. The errors cannot spread. So for this reason, it turns out that you need not to do very many rounds of error correction. Moreover, now this kind of, you have this possibility to do this long-range direct connection between logical qubits. It also can result in savings, but in particular, from the point of view of the control, this actually really makes a transition from control over single physical qubits to controlling these patches as a basically kind of macro atoms. So each patch now can be controlled with a certain set of laser beams. And all of the atoms within this patch receive the same instruction. They act kind of like as one big kind of atom, essentially. Okay, to kind of illustrate it, so let me just show some experimental results. So here what we'll do logical synod with a surface code. And what we'll do, we'll prepare one of these qubits in a state X and another one in state 0, and then just perform synod. And the way how it's done is, for example, for this small 9-atom distance-free code. So what you can do, you can basically just measure Z stabilizers for one of these qubit, for one of this patch, measure X stabilizers for another, and then just bring them on the top of each other. Entangle, basically separate, and then just measure to see if entanglement was created. And this is a small distance equals 3 patch, but we can also scale it to D equals 5, and actually and distance equals 7. So up to now, basically in other platforms, people were able to create distance 3, 1 qubit, and distance 5 only. So here now we're entangling them. And so, for example, here, by looking at distance 7, by measuring these 2 qubits on XX and ZZ basis, clearly, we see that they entangled. And moreover, if you look at the error in this entangled bell pair as a function of code distance, clearly this error decreases. So that's a key feature of error correction. So basically, it's actually quite non-trivial. So you make a larger entangled state by going to larger patch. You make a larger entangled state, but it becomes more robust. That's a key idea of error correction. So there are different kind of caveats here, which is worth discussing. So for example, this positive result were obtained only if we decoded these two patches jointly, where we didn't look just at sort of try to detect errors in one and another separately. So it turns out that by looking at them together, it's actually decoding works much better. And if I have time, I will return to that. It turns out to be like very, very important and kind of, I would say, almost fundamental aspect. The other maybe caveat here is that we just did one round of error correction. So it's actually in practice, of course, you need to repeat them and do many rounds. But nevertheless, it's clear that this experiment demonstrates a key feature that basically entanglement and quantum operation improves with the size of the system. And also this correlated decoding points out that this actually, not just engineering, it's actually exciting scientific frontier. So, and I will actually comment on the implication of that if I have time at the end. Okay, so that's kind of a key idea. Maybe I can maybe also slow down and ask if there are any questions. Yeah.
Beyond the conventional decoding, you get some threshold, and is that close to the threshold that you get with coordinates?
So, I mean, you want to do as few rounds if possible. And maybe the right question to ask, is there a threshold for one round? So conventional, if you would ask a year ago, you would ask that basically everyone working in the field, they would say no. So it turns out this is incorrect. It turns out there is a threshold. And actually, maybe if I have time, I will talk a little bit about it. So basically, it turns out that this actually is a general result. So if you do transversal gates, which don't spread errors, and if you decode jointly, you can actually perform universal quantum computation with about one round. And if you decode jointly, yeah. And the threshold, at least the cases which we tested, is not very different from sort of conventional. Yeah. No, it's actually a feature. And I will actually, so the kind of fundamental idea here is that what I already said is transversal gates, they don't, the errors don't propagate. And so in a way, the errors propagate deterministically. So if you had an error in one, so if you decode and you found an error in one patch, if you use like a hyper edge, you can check if there was an error on the other patch, and that's a new information. So, yeah, and it allows you to basically greatly reduce the number of syndrome measurements. Yeah, yeah.
All of the physical physics of what one we have. So,
yeah.
And it gives you does that atom have very low energy vibrational modes that might be excited by this process of bringing different logic pieces together and letting.
Yeah, so indeed, so if I understand this question correctly, what happened, like atoms have an internal electronic degrees of freedom, which we can control. There is also, the atoms can also move. And actually, in general, we do not cool atoms to absolute lowest motional ground state. And here, this idea of blockade turns out to play a very important role, right? So normally, if the atoms would move, right, and if we bring them together, they would, like the interaction strength between them would oscillate, and this would result in imperfections in this entangling logic. But because we use blockade, basically our interaction is almost digitized, right? It's either nothing, or if they bring them together, it's basically infinite. I mean, to the leading order. And that allows us to do what we do, right? So it's actually to the leading order insensitive to this motion, yeah. Okay, so let's now kind of based on this, kind of things, let's try to do things, kind of increase the complexity a little bit. So what we now kind of, at least in our mind, we're now entering this era of early fault-tolerant quantum computation, where we start building and kind of testing logical processors in the lab. And so what that really means is that, but like the resources are now limited, right? So if we really want to make a progress, we have to think about the problem we want to solve, for example, simulating matrix mechanics in a black hole, together with some optimized error correcting codes, and also with optimized decoder. As I already pointed out, decoder is very important, optimized compiler, and eventually it has to be co-designed with this kind of negative hardware possibility. So, by doing that, you can really circumvent orders of magnitude in sort of requirements and actually accelerate the progress by years, if not decades. So let me give you one example. It's admittedly still a very much toy example, but already kind of an intriguing example, in which we implemented this non-local, so-called non-local Clifford operations. So it turns out that for 2D codes, like basically the gates that you can implement transversally are all the so-called Clifford gates, like X, Z, Hadamard, C0. And if you build a circuit from Clifford gates, you can create a lot of entanglement, but the output from the circuit can be simulated very efficiently classically, because just operators under Clifford circuits, operators don't spread very much. So you can control basically, you can calculate, look at spreading of the correlations at operator language. So in order to make these circuits hard classically, you need to add something which is called quantum magic, and this is due to non-Clifford operations. So in general, to create this magic is actually challenging. So for example, some of you have heard about this T-gate factories, T-gate distillation. There are some kind of ideas you can try to switch back and forth between 2D and 3D code. But so we asked the question, okay, suppose we don't want to go general, we want to implement certain specific circuit, and we want to have a lot of magic. Can you do it? So it turns out the answer is yes. And you basically need to go to the 3D code. And actually, the smallest kind of non-trivial 3D code is the 8-qubit code, where these qubits are located on a cube, like shown here. So it's actually, it turns out in this 8-qubit code, you can actually encode 3 qubits, and the distance is 2. So it's actually, it turns out it's an error correcting code for one type of error and error detecting code for another type of error. So we need to do some post-selection, some error detection. So, but the nicest thing of all is that at this point, for these encoded qubits, you can create non-Clifford gates, for example, CCZ gates. In this case, within a block, you can just perform like some phase shifts, some T gates on individual qubits, and basically that creates a CCZ gate within a block. So what we will do using this insight is we will start building kind of circuits in which we will encode, we will create logical states plus, then perform the CZ and CCZ interblock, then using the motion, do C-knots between the blocks, and then repeat it in many many iterations. So it turns out that like you can do different things, but what we have done, we decided to kind of create, hypercubes. So basically, to begin with, so we have cubes of physical qubits. Then from these cubes, we create, higher, order cubes and proceed it in this way. And basically, what it really means, if you look at physical connectivity, it actually becomes very complicated. And that's the kind of circuits which we will implement. So using this connectivity and using this procedure, it turns out implement something which is called IQP, instantaneous quantum polynomial circuit, is actually an example of fast scrambling, classically hard to sample a circuit for large number of qubits. And so we can now use it as a test case to see how well, in this case, error correction and error detection will work. So basically, we'll do sampling here. So we'll prepare the state and just measure it in a certain basis. And here you typically get some kind of like a bit string. So this curve, which is hard to see, is actually an ideal distribution. But you see, for example, that like this ideal distribution in theory is for small number of qubits, which you can still simulate efficiently. This raw output, is actually, doesn't really look like the real distribution. But actually, if you now start, using, in this case, error detection by conditioning on more and more stabilizers being, correct. So what you see basically a shadow of the perfect distribution, which appears in your kind of post-selected samples. And you can basically quantify it, by, for example, looking at fidelity. On this case, is logical cross-entropy benchmark. So 1 is perfect. And so basically by improving error detection, you kind of, this approaches unity. So what you see is that basically the results with this error detection are closer to this ideal state. And we can now start asking various type of questions. So for example, you can ask, if you do this error detection, what errors look like? So it turns out errors are digitized by this approach. We can also ask a question of scaling. So what if you go to larger number, larger circuits? And so we went to 48 logical qubits. So this actually is a logical circuit. It's a circuit with logical qubits, which we implemented. And for this circuit with this kind of a bit crazy connectivity, if it would be in 2 dimensions, so we actually, it's still this error correction, or in this case, error detection performs quite well. And actually, you get a fidelity which is, like 10%. So this really shows how one could start kind of using this type of techniques to, for example, doing some kind of complicated algorithms. So this is actually a movie showing how we actually create this kind of entangled state. What you see in this movie, you first entangle qubits locally, and then you start more globally and more globally, and eventually we run out of the sites in the entangling zone. So we store the qubits, take another patch, and then entangle locally, and then entangle more globally, like this, and even more globally. And then in the last step, we will just entangle them all. So you can now start asking, what can you do with this? And what we kind of, as I already mentioned, we like to measure entanglement entropy. And so actually, it turns out, you can do entanglement entropy measurement with logical qubits also. And for example, what you can do, you can just take 2 copies of the state and just do transversal CNOT between them. So this is, for example, a circuit. You first scramble them independently and then do this Bell measurement. And what you see here is this kind of almost classic, I guess, page curve is in a time domain, right? But it's kind of something like a page curve. So basically what it shows here is that, this as a function of subsystem size, this state is completely scrambled, and it's scrambled very efficiently. It's actually a fast scrambling circuit. I don't think it has anything to do with black holes, but it's still a fast scrambling. But so basically, normally, if you wouldn't do this error correction, error detection, if the system keeps growing, even beyond half of its total number of qubits, the entropy increases. But here now, if we start using error detection, so what you immediately see is that once you reach a half system size, it starts coming down because the global state is really pure. So this actually really shows, how one could start using these logical qubits to really probe the physics of complex entangled systems. And I think it's really an exciting scientific opportunity for this kind of early fault-tolerant processors. So does it make sense? I have a couple of Outlook slides, maybe. Any questions about yes?
I thought that there was a trouble measuring too large entanglement. I mean, the way I was aware is that there's some parity that you measure, and but I see that here you can measure like 8 units of
yeah. No, that's precisely. So usually the challenge, so this entanglement entropy, for example, like as Mikhail was talking in the morning today, this topological entanglement entropy is like an amazing kind of observable. But the trouble is in practice, it's not a good observable because if your system becomes larger, and for example, even suppose your initial state is perfect, but your measurement has some small imperfection. So this small imperfection in measurement adds the entropy, which is basically proportional to the volume, right? So basically, it becomes very hard, beyond small systems to measure entropy simply because the global state of the system is mixed now for whatever reason. So, but here, once you start utilizing this kind of logical qubits, this is precisely at the last step. What you do, you decode the information, you do either error correction or error detection, and then you basically purify the global state, right? And that's the key, right? So basically here at the end, so what this measurement shows is that, the global state is basically nearly pure. right? And that allows you to now look at subsystems and really use this entanglement entropy as a meaningful quantity. Does it make sense?
Yes, but so are you measuring second gradient entropy or what?
Oh, yes, we are measuring. It's a 2-copy measurement. It's a secondary, exactly. It's a bell. So what we literally do, we take 2-copy states, 2-copy, and then basically measure each pair of qubits and copies in a Bell basis. And you can extract the second order entropy. Yeah. Sorry, which circuits? Yes. We actually, I kind of skipped it, a little bit, but yes, indeed, we have done things. For example, we did like experiment of logical teleportation. So where we did an emit circuit and they did feed forward. Actually, I have some maybe slides here that I'll show you a little bit. Yes. And of course, we also have ability to make multiple rounds, as well. Yeah. Yeah. Yes, exactly. So in this specific experiment, because the code distance is 2 along 1 for 1 error. So what we have to do is indeed in the last. So we'll run the circuit and then we check stabilizers, right? And basically, if some of the stabilizers, if like flags, they go off, we have to throw away these samples, right? Huh? We correct one type of error, but for another type of error, we have to throw them away. So, and it's of course, this error detection is eminently non-scalable procedure. But nevertheless, for experiments like this, for sampling, it actually pays off. It actually increases signal to noise ratio. And the reason is, so like if you have, few perfect samples, you can do, for example, this Bell test and so on. It's much easier to do if you have a lot of samples which are very bad, because then your purity, you see what I'm saying. So for this circuit, it actually pays off. But of course, eventually you would like to use error correction. But I would say at least kind of in a foreseeable future, you would like to actually do both. You would in fact do both, right? You use whatever you can, right? Yeah. All right. Okay. So I have a couple of slides for maybe an outlook, and actually some of them are addressing some of the questions which have been asked. So this kind of correlated decoding is something we discovered was almost like a necessity, because without correlated decoding, this Bell experiment with surface code did not work, and it actually resulted even in some discussion in the quantum error correction community. To what extent is it really a legitimate way to do it, or do you guys do something funny? So we actually now have most answers to that. And just to kind of maybe remind you what is, so like if we do these transversal gates between qubits sitting on top of each other, what will happen is that if you have certain errors on like one of the patch, they will propagate to another patch. And certain type of errors on another patch will propagate on a top patch. But this error propagation, which normally is like a real disaster for error correction, here this error propagation is localized. So what it really implies is that if we now start decoding, we can really think about this kind of hypergraphs where these different sites which were connected during the gate are connected by this kind of hyperedge, and actually this information turns out to be super useful to basically to improve decoding. And we have done it all with these Bell states. We actually also have done it. We created GG states, for example, of logical qubits. And there is also an error propagation. But again, this propagation is deterministic. You can really utilize this information. And so basically, the kind of insight here is that you can really undo error propagation by tracking the errors to improve this decoding performance. But of course, if you do like many rounds of error correction, the errors will build in time. So there will be entropy. So you need to extract entropy. So basically, quantum error correction is only about extracting entropy. But actually, it turns out that if you, again, build the circuit correctly, you can use this correlated decoding, even if you do multiple rounds in a kind of very efficient way where you basically, it's enough to have, one or sometimes even a fewer than one stabilizer measurements per CNOT. And basically, and this, decoding, performs extremely well. So it has thresholds and everything. So, and so this kind of already results, for example, in a factor of D reduction, because you don't need, normally you need to do D rounds after each step. So it's actually, interestingly, so this was sort of something that people would kind of believe was possible. Actually, it turns out that this conclusion is more general. So it's not only limited to these Clifford circuits. So it's also the case if you, for example, do like this kind of magic key injection where you actually can do non-Clifford operation. So, and this is kind of a new major theory development, which was sort of, inspired by our experiments called algorithmic fault tolerance. So basically, what it really shows is that, if you do the complex gate sequence and even do like mid-circuit measurement and feed-forward teleportation, so long as you sort of do it correctly, if you decode jointly and if you update your sort of decoding result as you gain more information, you basically, with one round, when you do transversal gates, it basically follows threshold behavior. So basically, that's a conclusion which is emerges from these studies, and it's actually has important practical considerations because it allows to like at least a factor of 100 speed up in sort of any realistic large scale computation. So that's kind of one type of things which we are working on. So we are also trying to use these tools which we have sort of developed to also do some interesting kind of near-term quantum simulation experiments. So this is one example, was somewhat inspired by the morning lecture by Michael. So here what we are trying to do is we are trying to basically explore topological phases in the so-called Kitaev honeycomb model. So that's this model with this anisotropic spin interaction, XX, YY, and ZZ. So it's actually normally it does not kind of naturally occur in materials, but but it's actually a very interesting model because it basically has a lot of symmetries. For example, this Hamiltonian commutes with this six operator product kind of stabilizer, and actually for this reason it actually can be exactly solved by mapping to Majorana fermions. And in this model there are both abelian and non-abelian phases depending on values of these coefficients Jx, Jy, and Jz. And of course, using this kind of reconfigurable architecture is actually relatively easy for us to realize it. All we need to do, we just need to do ZZ gates, between different neighbors, but turn the basis, from Z to X to Y in between. And so using this kind of stepwise, the so-called Floquet approach, one can actually implement the Hamiltonian of this type. And so basically, we're now already starting to explore this kind of model, and this actually shows how we can use different tools. So actually, the way how we prepare the low energy state of this Kitaev model is we first make a measurement of these 6 operator stabilizers, and this is done by essentially kind of moving qubits around by just creating a circuit that touches different qubits here. So in fact, we realize the state here on a cylinder because theorists like the cylinders, So, and then by measuring this qubit Smith circuit and basically figuring out, where kind of anyons are and pairing these anyons. So we basically can create a abelian topological state. And then from this abelian, we can actually basically use this kind of, sort of shortcut kind of adiabatic inspired trajectory to go to this non-abelian state. And basically create fork break time reversal symmetry, kind of create an interesting, phase here and start making some measurements. So it's very much work in progress, but I can already saw some of the first results. So here is, for example, this blockade parity, which really indicates a project, the presence of this topological order. And what it shows you, so these gray results are just raw values. And what you see is that, as you do, the circuit is not super long circuit, super deep, but it's, 10 layers of gates. The errors accumulate, this parity goes down. But now one can start using these tricks, this error correction and error detection, which, this topological state has kind of intrinsically to really try to kind of improve there. In fact, this is like the best sort of error corrected and error detected parity, which actually barely drops as you do more and more gates. And it's actually a very nice platform to start probing on abelian nature, measure gap, think about braiding. So this is also actually a very hardware efficient way to do digital simulation of fermionic system, which actually normally is challenging. So it's not the cheapest in terms of number of qubits, but it's actually the cheapest in terms of the ways how to actually build this fermionic system. Simply, the idea here is that in this Kitaev model, it's exactly integrable in terms of Majorana fermions. And of course, Majoranas you can pair to make real fermions. And that's the kind of approach which we are pursuing. Yeah. Yeah.
In the Kitaev model, you have 3 terms in Hamiltonian simultaneously.
Yeah.
By the way you move around the Rydberg atoms, like you just alternate for one.
Yes, yes. So it's kind of, and we do like the actual circuit here is we do many of these small relatively small phases, right? And it's kind of, it's a little bit like yesterday's talk was about Trotter. Remember, it's not. It's actually, you can, for a given problem, you can optimize it in a highly efficient way. So in practice here, to actually evolve to this non-abelian state, you only need about 12 layers of this operation, it turns out. So by preparing abelian state, so we prepare abelian state by measurements. So, and then this circuit, which is actually shown here, which is basically, involves these different phases, and sometimes these phases are larger, sometimes are smaller, but basically it's now optimized to reach this state in the fastest possible way, right? So, and of course, like this model is integrable, but now you can add the terms which break integrability. So it's sort of a very nice playground, and for example, one can also start measuring things like topological entanglement, entropy, and all of these things here. Okay, so I want to kind of maybe conclude just by, kind of with the outlook about, what are the other things we are working on. And so I would say with these developments, this kind of medium scale logical processors really appear within quite direct reach. So there are already, a couple of experiments, including in our labs, to scale up to maybe something around 10,000 atoms. And these improving errors will never stop. But I would say these 3.9 error rates are very much now within the reach. So there are these unique opportunities already. I mentioned a little bit erasure. So sometimes we lose qubits. So we now learn how to kind of, how to not just correct these qubit loss, but also how to utilize it. And so with all of these developments, I would say there is a quite direct path to devices with maybe 100 logical qubits and maybe 10 to the minus 6 logical error rates. But already there are ideas to kind of go beyond. And there are, for example, people are working on this quantum LDPC codes to include the encoding density, better ways to trap atoms, better ways to control, going beyond the AODs. But I would say with all of this, the approaches to 1,000 qubit logical devices are certainly, no longer a science fiction. But to kind of show you a little bit, kind of that is a phase transition. So this is a circuit that students drew in the lab. So it's actually a logical GHZ state. I didn't talk about these results, but you can believe me now that we can create, so, and actually each line here corresponds to a logical qubit. So they're thinking in terms of logical qubits rather than physical qubits. And I think this is really, very exciting. So, okay, so I think I've used up my time. So I would like to thank you for your attention and thank all of these people whose blood and sweat resulted in this work. So thank you very much. Happy to answer any questions.
Say a bit more about how the losses are detected,
About what?
the atom loss detection.
Yeah, so yes, so the question is basically the following. So as we do the circuits, in each, when we have, for example, a CNOT gate, there is a small probability, and right now it's about 0.1%, that one of the atoms is lost. So, and if not taken into account, then eventually you lose all atoms. So there are basically two things which you have to do to circumvent it. So first off, three things. So first off, you need to detect whether the atom was lost or not. And this can be done, if you measure, either you measure ancillas, or for example, if you do like logical teleportation, if you measure the qubit itself, logical qubit itself, you can resolve, if you do it correctly, you can resolve whether qubit was in a state 1, 0, or it was gone. And so at this point, you can utilize this information to, for example, decode better what happened during your gate. So this so-called loss decoding turns out to be very important. It's in particular very important if you do multiple rounds of error correction. So, but of course, then you could ask, well, wait a second. So if you do this if you just measure ancillas, you might have lost a data qubit. How do you know that it did not happen? So, how to handle it is actually turns out to be algorithm dependent. In general, what you could do is you can occasionally, for example, map, what you where you use your ancillas, where you use your data qubits is kind of your choice. So you can sometimes teleport your data into ancillas once in a while and then measure, now make a measurement of what used to be your data qubit. But actually in practice, and this is a generic approach to solve this, this kind of, it's called sometimes swap trick. But actually in practice, our understanding is that you almost would never need to do this, because you can build the circuits in such a way that you can always basically make the measurement of data qubits early enough to decode this thing correctly. And actually, while it's a challenge, it's also an opportunity. If you know that qubit loss is lost, you can sometimes convert it into so-called erasure error, which actually has much higher threshold. So, and this is actually, you can improve your decoding in such a way that your threshold actually goes up even. So, yeah.
So with 1,000 logical qubits and errors of the order of 10 to the minus 6, you're not far away from being able to factorize numbers. So how far away?
No, I think it's okay. Well, okay, so using current estimates, I think you need billions of, millions of operations. It's roughly an n cube, right? So logic, yes. Yeah, that's right. But the number of operations is n cubed for Shor's algorithm. So that means that you
10 to the minus 6.
Oh, well, there's a difference between 1 million and 10 to the 9. But of course, there is these ideas. For example, there is a Getz algorithm which potentially can bring this down. So it's not. I would not think that you are in imminent danger. You can still use your bank cards, but I think this gap, I can imagine this will start to narrow. But I think it sort of needs to be done from both sides. Algorithms should be improved. Maybe, maybe encoding should be improved. I think this kind of code design, I actually, the more we doing work along this line, the more I'm convinced that this code design approach will be absolute key, maybe forever, but certainly in the near term, certainly in the next 5 to 10 years. And you cannot, either thinking about, algorithms, in particular digital algorithms, kind of in abstraction, without thinking about what error correcting codes you will use is really not, I think is not very fruitful. I mean, you have to start somewhere, but I think the most progress will be made with this idea of sort of improving all of these things together and to kind of match them to actual the hardware platform.
Maybe a related one. So what about the matrix models that one was proposing?
So this is, well, I think there's actually, today I had lunch with some of your postdocs and sort of I hope I inspired them to, so my understanding that these matrix models, they require maybe thousands of qubits and number of gates is maybe 10 to the, 6? 10 to the 8, so which is challenging, right? But there are a few caveats. So first off, my understanding is that what's interesting there is to go to relatively low energy state, but not to absolute ground state. All of a sudden, this is a very different kind of beast, right? So, and in fact, for quantum simulations, you almost always don't need to sort of go to absolute ground state. You just want to have, low enough temperature. So I think some of these ideas, maybe even error detection can be in this case scalable, right? Because error detection is exponential if you really want to have absolute no errors. But if you're willing to tolerate some number of errors, all of a sudden it opens a lot of doors. Moreover, for example, my understanding is limited, but I personally think maybe one shouldn't think about qubits at all. Maybe you should think about encoding matrices into some kind of, error correcting codes, And so, for example, these QLDPC codes have a little bit of this flavor, right? Because they're still qubits, but they're all over, And, but the types of operations you need to do are only very certain type of operations. So most of algorithms do not require absolute universal, kind of logic and so on. They require just certain sets. So I think kind of thinking about this code design for this Juan's model, I think is super interesting. And I think this is, absolutely, I think this should be done, And maybe this could be, then one could bring it to the point that is actually very realistic, So. But one should not think about these things in isolation. And I think it's a real opportunity,
There are no more questions. Let's thank Misha again for one.